And I'm Brendan Avent. I'm a PhD student at the University of Southern California, and I'm here today to talk to you about our project, Blender, enabling local search with a hybrid differential privacy model. Sorry about that. Hopefully this will be better. So this is joint work with my advisor, Aleksandra Korolova, also at the University of Southern California, David Zeber and Torgeir Hovden at Mozilla, and Ben Livshits at Imperial College London. I want to start by talking about the problem that motivated this project, which is local search. In a typical simple web browsing session, users pose queries to a search engine and receive a list of results in the form of relevant URLs. With local search, the idea revolves around the problem of how a browser maker can collect information about browsing habits in order to create the head of a search log. And this is basically a list of the most popular queries along with their corresponding most clicked URLs. So this head list can then be stored locally on users' devices as a form of caching, and this gives several advantages. The most obvious advantage is that it can avoid many round trips to a server. If a user wants to make one of these head list queries, then results can be returned to a user instantly from their device rather than having to make a round trip to a server. So the only time you need to make a round trip to a server is when you make a query that isn't in the head list. So this obviously makes browsing sessions more efficient by reducing latency, but it has some other benefits. Imagine you're, say, in a rural area with poor internet connectivity, or you're using your cell phone with spotty data connection, or you're me in the hotel room yesterday where the Wi-Fi seems to cut in and out completely at random. You can have a much smoother browsing session with this head list served locally, because if you're making any queries, you can just get these results back without having to reach out to the server. So it kind of smooths out these temporary internet disruptions. Local search also has the possibility to enable new browser features, such as sourcing content from multiple search engines, depending on the context, or even in combination with a user's own browsing habits to perhaps intelligently preload web pages for a user. And while local search is great in and of itself, we're more interested in local search with privacy. But why do we need privacy for local search? Well, at its core, local search has this head list, which is generated based on user data. And in fact, that user data is a user's search history. User search histories are extremely sensitive, and it's mostly considered one of the most sensitive pieces of data that the average user has on their computer. So if they're going to give that up, they're going to want some serious privacy guarantees to go along with that. In fact, more than just serious privacy guarantees, they want rigorous and quantifiable privacy guarantees, which implies that we want differential privacy with local search. Now, especially after having just heard the last talk, I'm not going to go into all the details about what differential privacy promises and the kind of things that you can get out of that. But I will very quickly mention that the differential privacy definition that we have is this epsilon delta definition of differential privacy. In a nutshell, all it says is that a randomized algorithm is differentially private if the algorithm isn't very sensitive to changes in one user's data or a small number of users' data. But what makes local search with differential privacy hard? To understand that, we have to look at the two major models that differential privacy operates in. That's the trusted curator model and the local model. In the trusted curator model, all of the users send their data to a central curator who performs some sort of privatization along with their analysis before releasing the results. Most algorithms that you see in differential privacy, both in literature and in practice, fall within this trusted curator model. But it comes at the obvious drawback that users have to actually trust the curator with their private data. And that is, they have to trust that the curator will not be leaking any of their private data, either directly or indirectly. Directly in the form of security breaches or subpoenas or nosy employees, and indirectly through computations that are done on the data, whose results are then subsequently observable and analyzable. So to address this drawback, the local model allows users to privatize their own data before sending it to a central curator. So the central curator only has access and operates only on this already privatized data. So any breaches at that point are on the privatized data and not on the user's actual underlying data. This obviously requires much less trust from the users with regards to that central curator. But experimentally and theoretically, it's been shown that there are some serious utility trade-offs when using local algorithms. Specifically, if you want to achieve the same level of utility with a local algorithm when compared to its analogous trusted curator model algorithm, you need significantly larger amounts of data, sometimes prohibitively so. So we're interested in creating a model that combines the strengths of both the trusted curator model with the local model while minimizing either of their weaknesses. Moreover, we'd like to somehow take advantage of the fact that different users have different preferences when it comes to their privacy. In particular, many companies rely on a group of beta testers with whom they have higher levels of mutual trust. And it's not uncommon for such beta testers to voluntarily opt in to a less privacy-preserving model than that of the average end user. So our hybrid model for differential privacy that we're proposing is very simply one that allows some users to contribute to the trusted curator model and others to contribute in the local model. These trusted curator model users are these beta users or power users, really anyone that trusts the curator with their data. We refer to them as opt-in users throughout the rest of the talk. The local model users are basically everyone else. These are the people who either didn't explicitly opt in, or they're maybe the people who simply trust the curator less with their data. And we refer to them as clients. So why do we want this hybrid model? Why not just use one of the other two models in differential privacy? Imagine we have a user base consisting of a large group of client users and a small number of opt-in users. What are our options for performing differentially private data analysis while still respecting each group's privacy preferences? Well, one option is we can just say we're going to go ahead and use the trusted curator model on these users' data, but that limits us to only using that small opt-in group of users. So that might be fine, but the issue with this is that we know for any sort of data analysis or learning task, the more data we have, the better. And we've just thrown away a large chunk of our data by choosing this option. So instead, we can say, all right, let's use everybody and just give them all this highest level of privacy guarantee by treating them all as clients using the local algorithm. We can do that, but we know that the drawback to using local algorithm models is this harsh utility trade-off. So we're losing some stuff there. In fact, it's often the case that the only people who can treat users all as clients and use the local model are some of the biggest players, the Googles and the Apples, who have a significant portion of the global population as their user base. But what do we want to do when a smaller player wants to be able to analyze data in a differentially private manner? This is where the trusted model comes in handy. We can use both groups while respecting their individual privacy preferences without having to make any sort of compromises when it comes to the model we use. While this hybrid model seems like a great idea, it's just a model for differential privacy. It doesn't tell us how to, particularly for local search, how to use the two groups to generate data, or how to combine their data to actually improve our local search algorithms. So this is where Blender comes in. Within the hybrid model for differential privacy, we've developed an algorithm for actually achieving local search. The inputs to this algorithm for the opt-in group of users are their search records, and for the client users, it's their privatized search records. And the output of Blender should be a head list of the most popular queries and URLs, along with probability estimates for each of these records. So very quickly go over the architecture of Blender. It proceeds in 3 stages. The first stage is with the opt-in group. And the way this works is the opt-in group provides their data to a central curator. Central curator performs an analysis on it and produces a head list of these most popular search records, along with probability and variance estimates for all the records in the head list. In the second stage, the client group receives the head list that the opt-in group generated, and each of the clients in the group perform their own privatization on their search records, at which point they give the data to the curator, and the curator produces its own probability and variance estimates independent of the opt-in groups. In the final blending stage, the estimates for each of the records in the head list are combined together to form a final head list and final probability estimates for each record. So that's the high-level architecture. Now we're going to dive into how each of the individual groups' algorithms work. The Optin group algorithm works in a two-phase approach, a discovery and an estimation phase. It does this by partitioning the users into two disjoint groups. Group A, in the discovery phase, discovers the head list of the most popular queries and URLs, and Group B takes this head list and estimates the probabilities and variances for the URLs. And I should mention that we'll get to what the variances are for later. For right now, we'll just say that they're computing them. So the way the Optin Group A works for the discovery of the head list is very simple. All the users give their data to the curator, and for each distinct record that the curator sees, the curator computes an empirical probability for that record. It adds carefully calibrated noise from the Laplace distribution to form an empirical noisy probability. And then if that noisy empirical probability exceeds a very carefully chosen threshold, we add the record to the head list as a most popular query and URL. So that's all for Group A. Group A then passes on the head list that it created to Group B. Group B performs a very similar task. They all contribute their data to the central curator, and the central curator, in conjunction with the head list, computes an empirical probability for each record, adds carefully calibrated Laplace noise to form a noisy empirical probability estimate, and then finally computes the sample variance for this probability estimate. So this probability and variance estimate now are Group B's, or in fact the Optin group's, final probability and variance estimates. So the Optin group's algorithm is completely done in these two stages. The head list is then passed on to the client group, where each client receives a copy of the head list. The client then performs a two-stage k-randomized response, which is based on the randomized response algorithm discussed in the previous talk, so I won't go into detail on that. But essentially, the two-stage k-randomized response is an almost equally simple algorithm in that the client simply reports their query truthfully to the curator with some carefully chosen probability. Otherwise, the client reports a query from the head list completely at random. Stage 2 performs essentially the same action, but with URLs. So the client reports the URL truthfully with some carefully chosen probability, or otherwise, they report a random URL, which it corresponds to the query that they reported. So the curator then receives all of these privatized reports and aggregates them all together to form an empirical probability estimate for each record. Because of the nature of the client algorithm, the empirical probability estimates for each record that the curator now has are statistically biased in a known way. So the curator performs a statistical denoising procedure to generate unbiased probability and variance estimates for each record. At that point, the client group is also completely done. So both groups' outputs move on to the blending stage. The blending stage, essentially, for each record in the head list, combines the probability estimates of the records by taking into account the variance estimates for each of those probabilities. And what this does is it allows a final probability estimate to be generated that's in expectation better than either of the two groups could have individually generated. So at this point, Blender's final output is this head list of records and the combined probability estimates from the two groups. It should be noted that since each group computed their output in an epsilon delta differentially private way, the final output of Blender, or I should say Blender itself, is epsilon delta differentially private. The final main question then is, for these outputs and the applications they're used for, in particular for local search, how well does Blender perform? To explore this, we applied Blender on two real-world data sets, an AOL data set from 2006 of search log data, and a Yandex search log data set from 2013. These data sets basically contained users' search queries and the corresponding URL that they clicked, so exactly the data that we're operating on. The two data sets differed by about a factor of 10 in the number of users, with AOL having nearly 5 million users in the data, or 500,000 users in the data set, and Yandex having nearly 5 million users. The only way we treated these two things differently in our experiments is with the delta term in the privacy budget. And that was chosen based on the number of users in the data set. So the AOL, the smaller data set, was given a larger privacy budget of 10 to the minus 5, still small. And the Yandex data set was given a delta of 10 to the minus 7. The way we measure utility is through this idea of normalized discounted cumulative gain, or NDCG. This is a standard measure of ranking quality and information retrieval, and is often used to rank or measure the quality of search engine results. The way this is calculated is through this discounted cumulative gain concept, which essentially just adds up the absolute contribution of each query based on some predefined relevant score, and then discounts that according to its position in the list. So the relevant score for our queries are the probabilities, the true underlying probabilities of the queries. And what this score does is it basically says you want the higher the DCG, the better. And the way you can get that is by having higher probability queries earlier in the head list, or earlier in the list. This DCG value is an absolute sort of a raw score. So we want to normalize it by something to get a value between 0 and 1. So this is normalized by the ideal DCG. That is the DCG score if we had estimated the list perfectly. That is, if we had all the proper queries in the list and they were all in the exact right order. So this gives you the final NDCG value. For local search, though, we're not just dealing with a flat list of queries. We're dealing essentially with a list of lists, because we have our list of queries, and then for each query, we have the list of corresponding URLs that are most frequently clicked. So we need a more general concept than NDCG. So we use this NDCG of NDCG's concept. It's a pretty simple generalization. All it is basically for each query in the head list, we compute that query's URL list's NDCG value. Then when we go to compute the NDCG of the URL list itself, each query's contribution to the overall NDCG score is further discounted by how well it estimated its URL list. So if it estimated its URL list perfectly, then the NDCG score of that URL list would be 1, and there would be no discounting. If it estimated it poorly, though, then the NDCG value would be near 0, and the query's contribution to the overall NDCG score would be much lower. At that point, so that's the DCG computation. You normalize that DCG computation by the analogous ideal DCG to get your final NDCG of NDCG's value. Now, just keep things simple. I'm just going to refer to this from now on as the NDCG value, and we'll take that as a given. So at this point, we move on to our experiments. The first experiment that we wanted to perform was seeing how well Blender compares to having all users just use the local model, treating them all the same. To do this, we looked at the most recent state-of-the-art algorithm for accomplishing a similar task in the local model, and that was published in CCS 2016. What this did was their algorithm found the most frequent items in a set, and the way the authors tested this was by using this AOL data set that we're using, and they wanted to find the top 10 most frequently searched queries. They measured the NDCG score across a range of epsilon values from 1 to 5, and their results were NDCG scores ranging from 17.5% up to 38.5%. These were really good results for the local-only model, but what we consider for the local search problem to be usable in a practical sense are NDCG values in excess of 90%. So these weren't quite there, which is a typical problem with a local differential privacy when you don't have enough data. Running Blender, though, on the same data set, aiming for a head list of size 10, using only 5% of the users as opt-in users and the remaining as clients in the local algorithm, we were able to achieve NDCG results upwards of 96% for epsilon ranging from 1 up to 5. This was a massive improvement over the previous result just by using a small number of opt-in users. And it makes it's not only an improvement, but it makes it so that these results are now actually usable for practical purposes. There's a slight caveat that we used a slightly different NDCG computation in our paper than they did. But overall, it's not that much different, and we believe that this is a very fair comparison. So with this, we have this Yandex data set as well. It's much larger. We want to use that. On top of that, we're only looking at head list of size 10 here. What happens when we have larger head list sizes? Because that's what we want for local search. Moreover, we used 5% users as opt-in here, and that was sort of arbitrarily chosen. What happens when we change the number of opt-in users that we have? Because in practice, it's not something that we really get to choose. What happens if we have fewer number of opt-in users? How well does Blender perform then? So the question we then looked at was essentially, how does Blender's utility change as the opt-in group changes? And also, how does Blender's utility changes as we change the head list size? So we looked at, with fixing an epsilon of 4 and using the Yandex data set now, we looked at head list sizes of 50, 100, and 500 across a percentage of opt-in users that ranged from 1% up to 10%. As we see here, around 2.5% is where we start to get results that are above 95% on NDCG, which we consider very good. And after that 2.5%, we see increase in utility as the opt-in size increases, which isn't surprising. But what is a little bit surprising is that we see diminishing returns here. So this sort of implies that 2.5% is both a necessary and sufficient number of opt-in users for the Yandex data set for these head list sizes. And also another thing to note is that the utility did change as we increased head list size, but it didn't change it so much as to make a head list size of, for example, 500 unusable, with one slight caveat. At around 2%, at 2% less, the data for headless size 500 kind of stops. And this is because at this point, with this small number of opt-in users, Blender wasn't able to actually consistently achieve headless sizes of 500. So rather than the NDCG taking a hit at this point, it simply isn't able to generate 500. And that's the biggest takeaway from having a small opt-in user group. The next question we had is, OK, for different head list sizes, fixing the opt-in group percentage, what happens when we vary the privacy budget? And there's a lot of noise in these results, but the general trend is that as we increase epsilon, the privacy budget, the NDCG increases. Again, this is not that surprising. What is interesting to note is similar to the last slide, in that if we don't have enough of a privacy budget, for example, in the headless sizes of 10 and 500, we need an epsilon of at least 2 and 4, respectively, to generate the targeted headless size. So to briefly conclude, we've proposed a new hybrid model for differential privacy, which more realistically takes into account users' different privacy expectations. Within this hybrid model, we constructed a blended approach to achieving local search in a practical way. And it also achieved significant improvement on real-world data sets, which shows its practicality in real-world settings. And while this is great, Blender and the hybrid model in general still have a lot of work, a lot of research left to be done on them. For Blender specifically, all the subcomponents, the opt-in group algorithm and the client algorithm, are relatively modular. So we can actually replace those potentially with more state-of-the-art algorithms to achieve better utility, higher NDCG results, for example, or larger headless sizes. We'd also like to derive theoretical guarantees for the utility of Blender so that we don't have to run experiments to get an idea of how our utility will end up being in practice. We'd also like to reduce Blender's reliance on distributional assumptions, the main one being that the opt-in group has the same behavior as the client group. This can be a good assumption for many settings. Other settings, it's not quite, probably not the best assumption. So we'd like to see how to minimize this assumption or remove it entirely. And then finally, for the hybrid model in general, it's useful for more than just a local search or general frequency estimation tasks. So we'd like to see more algorithms developed to take advantage of these heterogeneous privacy preferences that users have. At this point, I'd like to conclude and thank you all for listening and open up the floor to any questions you may have.
Yes, thank you, speaker. Sumesh Chau, University of Wisconsin, really interesting talk. So the first, sort of a two-part question. The first question is it a crazy idea, and tell me if that is that you don't decide by users, but you decide that some users, for some URLs, might use the local model, and for some they say, okay, you know, these are URLs that are kind of non-controversial, and I'm just going to opt in. So opt-in is not per user, but by the type of the URL, so to speak.
Yeah, I think that's actually an interesting idea. I haven't considered that yet, but it seems like a research direction that could be taken, and Blender could possibly be used for that as well if you model the users differently, as you mentioned. So yeah, that is a...
And the second is, I think with the lower bound, I don't see, like, if you have a constant fraction that opt in and opt out, I don't think the lower bound I mean, in the worst case, you can just imagine that all the values will be in the local set. So the lower bound, I mean, I saw your future work. Lower bound can't be. I mean, I don't know what you were thinking of the second one. The lower bound would be the same.
For the theoretical?
As long as your constant division of 5% opt-in, 5% opt-out.
And you're referring to the theoretical guarantees?
Yeah.
Well, for theoretical, that may be the case, but for theoretical guarantees, we were more thinking things like, how did the statistical assumptions, using these statistical assumptions, what might our results be? If we deviate from the statistical assumptions a bit, what happens then? Also, just, we have theoretical guarantees for the local model. We have theoretical guarantees for the trusted curator model for the algorithms. So are the results, can we just combine those two guarantees in a way depending on the percentage of users? It's not entirely clear, but it might be. Thanks. Hey.
Hello, this is Thomas from University of Edinburgh. Very interesting work. I have more like a clarification question. Does Blender hide the predicate, whether you're a user that locally handles the privacy or delegates it to the curator?
So you're saying, is it sort of public information whether or not you're in the trusted?
Yes, is it something like a property which is leaked? And if so, is it something which is of a concern that should be addressed?
Yeah, that could potentially be addressed. It is not addressed in the model at all. So basically, it can be publicly known whether you're in the trusted curator model or in the local model. That's not something that Blender specifically uses, but that could be something that would be useful. I think the idea that you may have is that if a user wants to operate in the local model, maybe they have something more to hide, that sort of thing. And maybe that information should be...
this predicate, maybe it should be privacy preserved or not. Like if it is something like concern that should be addressed.
Right, yeah, so it's not, but I think that could be an interesting direction for future work, is how to mask those.
Thank you.
Thanks.
Aleksandra, Google. I'm wondering if it makes sense, rather than simply having a binary, I trust the curator or not, could you have some scaling thing where, depending on how much you trust, you either send the wrong result with 1% of the time or 99% of the time?
So this is within the local model only?
Yeah, within the local model only.
So I think that would basically come down to essentially using a different privacy budget for each user, similar to the question asked in the previous talk. Blender just uses a single privacy budget for each user, but it is conceptually possible that you could have users using different privacy budgets. I think that would also sort of connect back with the last question of, if you want a very small privacy budget, if you want high privacy, then maybe there should be a way to mask how that is done. Because if you want high privacy, the question is, why do you have something to hide, that sort of thing. And it'd be good to, if you're going to have different privacy budgets for different users, maybe a way to mask that would be something good to have.
Thank you.
Thanks.
Hi, Sebastian, University College London. The head list is basically generated by this group A of the opt-in users, right?
Right.
So did you play around with the fraction that group A is in comparison to group B to maybe overcome this limitation?
Yes, definitely. So that's one of the results that we didn't show here. One of the parameters is actually what percentage is group A and what percentage is group B. And what we found out through experimentation is that having most of the users in the opt-in group contributing to generating the head list gives the best utility. And then setting aside a small portion for group B for actually estimating those frequencies does a good enough job so that we can sort of maximize our NDCG results that way. Thanks.
Hello, Neelam Mevan from BC Cancer Agency. So I have just one question about experimental results you did. Mm-hmm. It seemed to have just one figure, but as far as I know, differential privacy gives kind of randomized accuracy, randomized results. So is it a median or average or something else?
Could you repeat the question?
So differential privacy, I mean, you achieve differential privacy through randomized algorithm, which gives a different accuracy when you run within same settings many times. So how do you report the results? Does it represent an average of number of times you run?
Right, so we ran it a few times for each of the experiments, for each trial. And what we did was we just averaged the results. You see some basically jitter in the results because there was a low number of trials and probably because of outliers from using the mean as our aggregation method. But hopefully that answers the question. Mean is the answer. Thanks.
Okay, one other thing. I just have a question. So a previous way to blend the local and non-local models in differential privacy was used before in works like PrivX and PrivCount, the authors of which are over there, in which you use the amount of noise you would use in the centralized model, but it's added by the individual users securely using a multi-party computation, right? So the trade-off is you have to have communication among the end users, but you get the utility you would have gotten from the centralized model. So,
yeah, that's it definitely is an interesting concept. It wasn't considered here,
right.
But it's definitely something that we'd like to look into more, and I'd love to discuss that with you all offline, if possible.
Okay. Any other questions? Let's thank the speaker again.
Thanks.